Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a course of lectures on semiconductors, as all of you know by now, and this is lecture number 8, and this is intended for the applied electronics students, and the paper is on physics of materials, and the syllabus is shown here, and the contents of the lecture 8 will be as follows: extrinsic semiconductors and the dopants which are used to make intrinsic semiconductors into extrinsic semiconductors, which will result in the so called N type and P type semiconductors, and the calculation of the donor ionization energy. Now, all of you know by now, when we are talking about intrinsic semiconductors, what do you mean by intrinsic? Pure semiconductors. You take pure silicon or germanium. As I have told you in one of the early lectures, germanium ruled till 1960. After 1960, silicon took over. Most of the applications that we have today in electron devices are based on silicon, silicon solar cells, and most of the materials are silicon based. Most of the devices are silicon based. Now, in the case of an intrinsic semiconductor, you all know that at any given temperature, the number of electrons you have got in the conduction band, this is the conduction band, and this is the valence band. The number of electrons you have got in the conduction band will be equal to the number of holes, because of the fact for every electron that goes from the valence band to the conduction band, a hole will be left behind, right. For every electron which is going from valence band to conduction band, there will be absence of electron in the valence band. As you see here, there are 8 electrons in the conduction band, and there will be equal number of 8 holes in the valence band. So, the number of electrons in the conduction band will be equal to number of holes in the valence band. Now, what is it we are going to do with regard to extrinsic semiconductors? Now, we are going to replace the silicon atom which has got valency 4 by a pentavalent impurity atom to make it as N type. By pentavalent means you have got 5 valence electrons. Out of the 5, only 4 are required for bonding purposes. The 5th electron does not know what to do. The 5th electron is the electron which will go to the conduction band, Therefore, for every single pentavalent impurity atom that is being added, there will be one excess electron, right. Supposing I put 100 arsenic or any pentavalent impurity atom, phosphorus or arsenic in the place of 100 silicon atoms, for every pentavalent impurity atom it is equivalent to adding one excess electron. So, apart from the fact that the electrons are going from valence band to conduction band by thermal process, because of the addition factor, namely the doping, for every dopant there will be excess electron. So, if I am putting 100 phosphorus atom or 100 arsenic atom, that is equivalent to adding 100 extra electrons. So, that makes the number of electrons in the conduction band to be larger than number of holes in the valence band. And so, because electrons are majority carriers, they are called the excess carriers, they are called excess carriers, and because electrons are majority, it is called n type, right. N refers to negative. On the other hand, if holes are in majority, it is called p type. Now, before going through all these things, we will go further with respect to the dopants. I showed you in the last lectures also, for silicon you dope it with phosphorus or arsenic to make it as because the valence is 5, to make it as n type semiconductor, because for every phosphorus atom there will be 5 valence electrons. Similarly, for arsenic also there will be 5, only 4 are required for bonding. So, one excess electron will be there, that will be sent to the conduction band. Our aim now to find where exactly what is the energy level in which the 5th valence electron will be found. That is the purpose of today's talk. That is the major objective that we have today, and how exactly we can calculate the energy level of the 5th valence electron associated with the phosphorus atom, wherein the phosphorus, as I told you, is going and occupying a substitution site which has been occupied by silicon. Similarly, you can have aluminum and gallium, they are the trivalent. The addition of or substitution of aluminum in silicon will lead to a hole, right, because aluminum got only 3 valence electrons, whereas the bonding requires 4, there is a one deficiency electron, whereas here in the case of phosphorus there is one excess electron. Okay. So, the objective of the major part of this lecture will be to find the energy level of the 5th valence electron in the n type semiconductor. So, as I told you in the last lecture, you can put the arsenic atom in the place of silicon. It is a substitutional impurity that should be remembered. It is a silicon lattice having number of silicon atoms, and one of the silicon atoms has been replaced by arsenic. What is the atomic number of arsenic? It is 15, right. Silicon is only 14. So, there is one excess electron. This excess electron will be revolving in a big circular orbit. So, this becomes like a hydrogen atom problem, because at the center you have got 15 protons, the atomic number of arsenic is 15, because you require 14 electrons for bonding, 10 plus 4, right. The valency is 4, for bonding you require 4, and so this dot refers to in principle 15 protons and 14 electrons. So, the resultant charge will be 1 positive charge. So, that is the reason why I put a plus sign here. So, you got a positive charge here, and the electron, the 5th valence electron, which is loosely bound, or it does not know what to do, because the fact the bonding requires only 4, the 5th electron is not needed. But anyway, the atom has got a 5 valence system, the 5th electron is bound to the arsenic atom, but it is weakly bound. Because of the fact that it is weakly bound, it is revolving in a bigger circular orbit. But how much it is weakly bound and where exactly it lies in the energy band diagram, all these things are to be seen. Now, as I told you, this reduces to something like the Bohr atom model. You got a positive charge here, something like a proton, and you got an electron. This is the hydrogen atom, but the two important things which are to be borne in mind are, in the case of hydrogen atom, you got a proton and electron. It is in vacuum, right? You got a proton and electron, but here also you got a something like a proton, a positive charge here, and electron here, but this everything is embedded in a matrix, in a silicon matrix, right. So, in a silicon crystal, So, these things, the electrostatic forces operating between the arsenic ion here and the electron here, it does not take place in vacuum, but in a silicon crystal which has got a definite dielectric constant. So, the definite dielectric constant that is possessed by silicon should be taken into consideration, and apart from that, you know, when you are talking about an electron moving in a crystal, in a crystalline lattice, in all crystals there is periodicity. The atoms are arranged in a periodic manner. You have got atom here, atom here, atom here. For every the lattice constant, for every complete lattice translation vector, you have got an atom here and then atom here and so on, right. Okay. Therefore, it is a periodic lattice. So, the electron is not a simply a electron moving in a constant potential, but it is moving in a periodic potential. The electron experiences a periodic potential, and therefore, the two important factors which are to be taken into consideration while calculating the energy of this electron. What is the energy with which the electron is bound to the ion here? You have got the arsenic ion here, with what energy the electron is bound. In the hydrogen atom, the electron is bound to the proton by what energy? What is the energy? It is 13.6 electron volt, all of you know. Now, similarly here you asked a question, what is the binding energy of this electron to the arsenic ion? Now, when you are calculating this, you have to take into account these two factors, namely the factor number 1, the interactions that I am talking about take place in a crystalline lattice which has got a definite dielectric constant. So, the dielectric constant should be taken into account. Secondly, the effect of the periodic potential should also be taken into account. Simply you cannot put the mass of the electron as m, you have to take into account the effective mass of the electron. Taking these two factors into account, one can calculate the binding energy of the electron. Now, these ideas were given first by Hans Bethe, and he was fortunate enough to be with the Nobel laureate Hans Bethe when Bethe visited the city of Madras in 1970s. It is Bethe who made the changes which are to be made when you want to calculate the energy of the electron with which it is bound to its parent atom in a silicon matrix. Now, so a complicated problem can be simplified to a first approximation. You can make approximations, right. The electron is revolving, and the revolving electron is something like hydrogen atom. You have got a proton here and the electron is revolving, and you want to find out binding energy, and again I have to mark the donor bound level in the energy band model. You have got a valence band, conduction band, and where exactly you have the energy level of this electron which is revolving around the arsenic ion. So, modified Bohr model to calculate the binding energy of the extra valence electron is extra electron, right, because only 4 are required. The fifth valence electron, extra valence electron of the pentavalent impurity atom revolving around the single positive charge of the arsenic ion. I will show the donor bound level will be here, right. The donor bound level will be just below the conduction band, right. It can be mathematically calculated, because based on the principles, based on the approximations which are given by Hans Bethe, one can calculate the donor bound level of the electron in the n type semiconductor. This is the energy level. What is ED? ED is called the donor ionization energy. What is the meaning of donor ionization energy? It is the energy required to break the bond. You got the bonding between the ion and the electron should be broken. Now, the energy is possessed by the electron, the fifth valence electron will be found here, and this ED is called the donor ionization energy. By donor ionization energy, what you mean is the electron which is found here can be given a small amount of energy in order to make it to go to the conduction band. So, this is the energy required by the electron to go from this bound level to the conduction band. Now, a very important question might come to your mind, namely the whole region is a forbidden energy region, right. You know, you got a valence band and a conduction band. In the band theory, we talk about forbidden energy region, the forbidden energy region. Now, how can you have an electron in the forbidden, the electron being the electronic energy level being found in the forbidden energy level, forbidden energy region, the forbidden energy region. In the forbidden energy region, how is it you can allow an electron to have its energy level? Now, you should remember only for the electrons of the host crystal, namely silicon, only those electrons will have energies in the valence band or in the conduction band. Only for those electrons the region is the forbidden energy region, but this electron about which we are talking now is not an electron from the host crystal, it is from the impurity atom, it is from the arsenic atom. Therefore, nothing prevents the electron associated with the arsenic to be found in the forbidden energy region. This is a very important point. One should not be getting confused as to why this level is a level which can be accepted, or this level which is found in the forbidden energy region, is it a energy level which can be allowed and so on, but this energy level is perfectly allowed, and this energy level is the energy of the electron associated with the impurity atom. This is not the energy of any electron belonging to the host crystal. That particular point is an important point. So, we will go through the assumptions once again. The 15 protons and of the nucleus of the phosphorus atom and the 14 electrons associated with the nucleus will result in a single positive charge. The lone loosely bound electron will revolve around the positive charge, as I showed you just now, and we want to calculate the binding energy. The problem reduces to that of the hydrogen atom. The two important changes which are to be effected, as I told you, are namely the electron is moving in a periodic crystal, in a periodic potential, one of the factors. The second thing is, I told you about the dielectric constant of the parent crystal, because it is not taking place, the movement of the electron in the arsenic is not taking place in free space, but in a crystal which has got a finite dielectric constant. Therefore, the factor of dielectric constant in the parent crystal, as well as the fact that the electron is moving in a periodic potential, these two are to be incorporated in the expression given by Niels Bohr when he was dealing with the simple hydrogen atom problem. So, taking into account these two factors, the radius of the electron which is revolving around the arsenic atom, the radius works out to be epsilon times h bar square by m e into E square, where epsilon is the dielectric constant of the crystal, and m e, what is m e? E refers to the effective mass. If I would have put m, simply m is the free electron mass. When the electron is moving in a constant potential, we put m. When the electron is moving in a periodic potential, we have seen in band theory, you come across the effective mass. So, I have put the effective mass here. And similarly, now the more important thing, namely the energy with which the electron is bound. I told you it is weakly bound, it is equivalent to now 13.6 divided by epsilon square multiplied by m e by m, where m e is again the effective mass. And what is m? M is the free electron mass. You know, the free electron mass, the mass of electron is coming in the denominator. Now, therefore, taking into account the two factors which I mentioned above, namely the electron moving in a host crystal having a definite dielectric constant epsilon, it is a dielectric constant of the crystal, and the fact that the electron is not moving in a constant potential, it is moving in a crystal wherein there is a periodic potential. Because the periodic potential, one has to deal with the effective mass of the electron, therefore, the effective mass will come into the picture. So, taking these two factors, the expression that we had earlier, it is only 13.6 divided by n square. We assume n to be 1, the electron is found to be in the lowest orbit, that is the reason why n is not being found, or n is has been made to be equal to unity. Okay. 13.6 electron volt is the energy with which the electron is bound to the proton in the hydrogen atom. But now, taking into account the other factors, now the energy of the electron now becomes 13.6 divided by epsilon square into me by m. This is the binding energy, right. Now, you substitute epsilon, the value of epsilon for silicon or germanium, then similarly substitute for me, the effective mass. Now, by substituting these things, you will find, what will you find? You will find the binding energy is not like 13.6 eV, but it is very small. It is something like less than 0.025 electron volt. What is 0.025? It is a thermal energy that will be possessed by the electron when it is kept at room temperature. KT is 1 by 40 electron volt or 0.25 electron volt, right. 0.25 electron volt is the thermal energy the system will have at room temperature. K into 300 will be 0.025 eV, but this energy will be much lesser than that. Let us now substitute. Me is the effective mass of the electron in the silicon crystal. The dielectric constant of the silicon crystal is 11.7. The effective mass is simply 0.2 times the free electron mass. Therefore, what I will do now is in the place of epsilon, I will be putting the value 11.7, and in the place of me, I will put 0.2 m, and m will be cancelled. You will be having 0.2 here, and epsilon square, a large value comes in the denominator. Therefore, the binding energy becomes much smaller. Okay. So, the binding energy will be something like 20 milli electron volt, right, 0.02 electron volt. Okay. The corresponding radius is around 30 angstroms. I gave an expression where the radius also, by substituting for epsilon and me, the radius is 30 angstroms, whereas in the hydrogen atom, what is the radius? It is around 0.5 angstroms. The electron is proton is here, the electron will be revolving in a circular orbit at a distance of 0.5 angstroms. But now, in this case 30 angstroms means what? Typical lattice constant of the crystals. It varies from 2 to 5 angstroms. They are the typical lattice constants. But now, your electron is revolving in a very big orbit encompassing 6 orbits, I mean 6 lattice constants, right. So, it is revolving in a big orbit. The fact that the electron is revolving in a very big orbit shows that the binding energy is very weak or very small. Therefore, the electron can be easily knocked out, or the binding energy is very small. The electron can be removed. Removed means what? It goes from the bound level to the conduction band. This gives the energy required to ionize the pentavalent impurity atom. By virtue of the atom embedded in silicon crystal at room temperature, it will possess an energy kT, which is 25 milli electron volt. 25 milli electron volt is 0.25 electron volt. Now, the electron has got in this case 20 milli electron volt, which is lesser than 25. Because of this factor, the electron will go from the bound electron will become a free electron. By virtue of the fact that it is kept at room temperature, it will 20 is less than 25. Obviously, the binding energy of the so called donor ionization energy is less than the above energy, and hence the electron will become a free electron and goes to the conduction band. Now, this energy with which the electron is bound to the arsenic atom is only 20 milli electron volt. What I showed you just now is 20 milli electron volt is the binding energy. By virtue of the fact that the crystal is kept at room temperature, the electron gains energy which will be 25 milli electron volt, which is much larger than the 20 milli electron volt. So, obviously, the electron will be taken to the conduction band will be gains enough energy to go to the conduction band. I think this should be clear. The binding energy is only 20 milli electron volt. So, therefore, because it is kept at room temperature, it possesses an energy 25 milli electron volt, which makes the electron to go from the donor bound level to the conduction band. This is called the donor ionization energy. The electron which is bound here, it goes to the conduction band. Okay. That is what we have to understand from the simplified Bohr atom model, which we have been using here to determine the two things, the energy with which the electron is bound and also the radius of the orbit in which the electron will be revolving in this case. And this is what I am again showing the donor bound level, the electron will be going from here to the conduction band. For every impurity atom that you are putting here, supposing I am having 100 silicon atoms are replaced by 100 pentavalent impurity atoms. For every pentavalent impurity atom, the fifth valence electron will be found here. Okay. So, by virtue of the fact that they are kept at room temperature, the arsenic ion or phosphorus ion will enable its fifth electron to go to the conduction band. If I am putting 100 pentavalent impurity atoms, it is equivalent to adding 100 electrons into the conduction band. I hope you understand this point. What I mean is, by putting a pentavalent impurity atom, the 5 valence system is there, only 4 electrons are required for bonding, the fifth electron is loosely bound, it is so much loosely bound, so that it can easily go from this level to this level. So, if you are putting 100 atoms in the crystal, there will be 100 electrons in the conduction band. Okay. So, there you will have what you call electrons as the excess carriers. Note the important point to be noted down. This energy level I am talking about now, which is found just below the conduction band, it is the forbidden energy region. This is what I told you earlier also. This energy level which lies in the forbidden energy region does not belong to the host crystal. Only the electrons belonging to the host crystal cannot be found in the forbidden energy region. So, this is a perfectly allowed energy level, that is the important point. We will now pass on to the summary session of this lecture. The N-type semiconductor is one which is obtained by adding a pentavalent impurity atom. On the other hand, a p-type semiconductor is one which is obtained by adding a trivalent impurity atom like aluminum or gallium in the silicon crystal or in the germanium crystal. The donor ionization energy can be calculated by modifying the simple Bohr atom model. N-type semiconductor will have excess electrons obviously. We have the question session. The question number 1, what are N and P type semiconductors? What modifications ought to be done in the Bohr atom model to calculate the donor ionization energy? Where do you find the donor bound level? With this we come to the end of this 8th lecture. The remaining things we will see in the lectures to come. Thank you.